Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 4.3.10. Binomial coefficients. We've seen how they've come from polynomials and multiplication, but they also come from coset counting. And that's exactly what this reading here discusses. It talks about counting things in terms of cosets. Another thing, let's just kind of go down to the bottom. You can look through the specifics of the text, but really it's a coset type idea. So if you even look at the formula for the binomial coefficient itself, it actually, this 4 factorial comes from the size of the permutation group on symmetric group on 4 things. And K, what's that? This is actually a group that fixes a certain configuration of boxes, kind of where we're trying to, we've kind of we have our boxes where we're trying to pick 2 things. We're trying to a box with 2 things, and you have another box with has 2 things. So you have these 2 boxes. Now K is a subgroup that actually, in the permutation sense, kind of fixes a particular configuration of the box. So like these boxes, like a permutation where what's in this box doesn't change and what's in that box doesn't change. Actually, there's 4 permutations that actually do that. You could just switch these 2, or just switch those 2, or switch those 2 together, or do nothing. There's 4 different things that fix that configuration. So K is a subgroup of S4, and really this is a coset counting thing, because how many cosets are there? Every coset has the same size. It's just a composition shift. They all have the same size. So that is nice for coset counting. So really, if you're even looking at this formula, you can almost think that this formula just comes directly from a coset counting of groups. Kind of a fun idea. You can take a look at this, and in general, multinomial coefficients come from such an idea. In closing, let's just take a look at one more idea from this section, a criterion for normalcy. Now, in this little subsection, basically, I mean, there's kind of a proof given in here, but the idea is it's a way of testing that you actually have a normal subgroup. One way of doing it is to see that the collection of left cosets is actually the same as the collection of right cosets. If you ever see that, it's not really true commutativity, but at least the collections of left and right, like as sets, as chunks, it chunks it the same way. If the left cosets chunk it the same way as the right cosets, then that actually is equivalent to being normal, so that the operation is preserved when we're chunking. You can take that as one form of it. Here's another form of it. If the left coset is actually equal to the right coset here in this particular case. So you can look through this example. There's an example of that if you'd like. Thanks for watching.